Okay, folks. So let's focus in here. Listen, yeah, here we go. All right, so we've got our new kind of behavior we're going to be looking at here called concavity, okay? And they're going to use the second derivative to analyze the concavity of a function, all right? So whereas increasing and decreasing is easier to kind of like pick out in a function, concavity is a little bit trickier, but, you know, it's not that much. It's just a little bit trickier, but not that bad, okay? So let's take a look at the definition of what it means to be concave, okay? Specifically concave upward or concave downward. So let f be differentiable. The graph of f is concave upward if f prime is increasing on the interval, okay? So that means, in other words, the slopes, and I'll put this here, the slopes of f are increasing, okay? And concave downward, so f we say is concave downward if f prime is, bless you, decreasing on the interval. That is, the slopes of f are decreasing. Yeah, no, that shouldn't be a y prime. That should just be like, I see what you're saying here. I'm trying to see. Okay, yeah, I guess we'll look at that. Yeah, we'll call this y prime there. That should be y prime there. Okay. Sorry, there's a typo there. It should be y prime right there for that graph. Exactly, yes. So a cubic here, okay, turns into a quadratic, which makes sense, right? Something cubed, its derivative would be like 3 times that thing squared, and then bring that 2 out front, and now it's just a line. So a cubic becomes a quadratic, becomes a line. Yeah. So, looking at this, all right, this is our original function. It's y, okay, and we want to determine the concavity of this graph, the concavity, all right? Well, what did we say? Concave upward is if f prime is increasing. So if I want to know where this is concave upward, I have to look at my derivative here to help me. And I want to know when is f prime increasing. So where is f prime increasing in this interval? 0 is where it starts to increase. This graph right here. Okay? So this graph is increasing from 0 to infinity. So therefore, if this graph is increasing from 0 to infinity, where is this graph concave up?
0.
Also 0 to infinity. Okay?
Oh, concave up.
Yep.
Okay.
Concave upwards or concave up is fine as well. So concave up from 0 to infinity. Okay? Increasing to infinity. Right, so the increasing f prime, or I guess call it y prime here, the increasing y prime, okay, is then leading to y, the original function, being concave up from 0 to infinity. Okay, the function is concave down if f prime is decreasing on an interval. Well, let's look at our y prime here. Where is y prime decreasing for what interval? Negative infinity to 0, right? Okay, so that's y prime is decreasing on the interval. So therefore, y is concave down, and again, you can say concave down instead of concave downward, that's fine. Okay, concave down for what interval then? What must it be? Negative infinity to 0, right? If y prime is decreasing on that interval, then y will be concave down on that interval. Okay? Now, why did I give this graph of y prime prime here? Well, second derivative further relates back to these two as well. So, for example, we said here that y prime was increasing from 0 to infinity. What's happening here from 0 to infinity? What's true? What's positive?
The function.
Y prime prime is positive from 0 to infinity. Okay? Likewise, here we said y prime was decreasing from negative infinity to 0. How is that showing up here? Y prime prime is what from negative infinity to 0? Negative. Okay? So, a positive derivative means our first derivative is increasing, means our original function is concave up. A negative second derivative means our first derivative is decreasing, means our original function is concave down. Okay? So you can see how we're going to use, or hopefully you can kind of see here how we're going to be using this second derivative test, right? When we wanted to find where a function was increasing or decreasing, we looked at its derivative. All right? If you look here, we're saying this function is increasing or decreasing on certain intervals, and that results in its derivative. Y prime is the derivative of y prime, right? Its derivative. The original is increasing from 0 to infinity because its derivative, y prime, is positive from 0 to infinity. Y prime is decreasing from negative infinity to 0 because its derivative, y prime, is negative from negative infinity to 0. Okay? For the concavity, right, it's relating these two things. So here we're relating original function and its derivative. Here we're relating an original function and its second derivative to get the concavity. Okay? So on which intervals is the graph concave up? Well, I already kind of answered that here, so I'll just kind of like boop right in there. Okay? And I also answer that right here as well. Shoot, I guess I should have just done this is concave up, this is concave down. Okay? So when we look at this, visually there, you see kind of like a valley, right? Okay? So you can think of kind of concave up as a cup. Okay? Concave up like a cup. Oh, sorry. There you go. And then concave down as and I don't know why there's an and there. I'm just going to put as a frown. Womp, womp. As a frown. Okay? Concave up like a cup. Concave down like a frown. Okay? Or people have said like umbrella. Or it looks like an umbrella. What's that?
Do you ever use convex?
Nope. Convex, yeah. Convex isn't included in this for some reason. I don't know why. Just concave. Yeah, it's probably an umbrella, I think is what it was supposed to be, yeah. But I like the frown because it rhymes with down. And cup kind of like rhymes with up, so it helps you remember it. Down is umbrella? Anyway, okay. So yeah, so let f be differentiable at C. If the graph of f is concave upward at C, f of C, the graph of f lies above. So this is kind of key, mathematician of concavity, okay? Because obviously, if you tell someone, oh, this is concave because it looks like a cup, you know, that's not very mathematical. But the mathematical definition is right here. Shh. Listen up, please. If f is, or let f be differentiable at C, if the graph of f is concave upward at C, f of C. So, for example, like right here at 1, the graph is concave upward, okay? 1 negative, 0.5, we'll say it roughly. The graph of f lies above the tangent line at C, f of C on some open interval containing C. So, for example, here, the graph is concave up right here, right? Like a cup. The tangent line, where would that lie? It would be below the curve, right? The tangent line is going to be right there. It will be below the curve. So that's how you can indicate that. Concave up, the tangent line is below the curve. Okay? Or you can say the graph is above the tangent line, whatever you want to say there, okay? So concave up, the tangent line is below the curve, or the curve is above the tangent line, however you want to say that. Number 2, concave down, so here's like concave down at -1, okay? F is below the tangent line, right? If I drew my tangent line right there, it would be below. The function is below it, or the tangent line is above it, whatever, how you want to say that there. Okay? So that's the mathematical kind of way to kind of indicate that. All right. Now on to how we're going to be like more doing that. So that's the kind of the concept. That's the big picture. Okay, so let's get more to the nitty-gritty. So the test for concavity. Okay, and this is the second derivative test. Okay, also known as... Oh, wait, no. Second derivative test is something else. Never mind. Don't worry about that. I apologize. This is just the test for concavity. Yeah, this is just a test for concavity. I don't on me. It might be some on my desk, but I think that thing ran out, and I don't have any more, so... All right. Since concave upward... That's right. I know, Anna, it's so sad that there's only that much time left in class. It's really unfortunate. I get you. Okay?
It's better than the other option. We could have one.
Concave upward means look, guys, this is a marathon. I told you we need to be prepared to go. And by the way, this is a shorter class than we had yesterday. So, okay. If you want to bring in cushions for your butts, that's fine. But this is a marathon. We're practicing. Okay. So, since concave upward means f prime is increasing and increasing, okay, means the derivative is positive. All right, so again, let me just kind of say that one more time. Concave upwards means f prime is increasing. How do we know that means that? Well, we just talked about that at the front of this paper, right? We were told that the graph of f is concave upward if f prime is increasing. So, since concave upward means f prime is increasing, and increasing means the derivative of that thing is positive, then f is concave up, okay, when f prime prime is greater than 0, when f prime prime is positive, okay? And then since concave down, or downward, which is fine to just say down if you want to, since concave downward means f prime is decreasing, okay, and if something is decreasing, that means its derivative is negative at that value, right? So f prime is decreasing, and decreasing means the derivative is negative. Okay, then f is concave down when f prime prime is what? Less than 0. Very good. Yes?
The only reason they don't talk about convexity is because concavity up is convexity down.
Yeah, I think so. I think it's basically it would be redundant almost. Concave up, concave down takes care of all the behavior that we would need. So I guess we could call it, convex down and convex up.
It's kind of hard to
Right. Exactly. Yeah, and there's no good rhymes. Or the rhymes would be wrong. It would be convex up like a frown and convex down like a cup, and that would be wrong. So they probably if this won't rhyme, it won't work. That's right. Those poor calculus students, they'll just never learn it. Okay, so let's do it. Find the intervals of concavity of f of x equal to x to the fourth minus 4x cubed. Okay, so Anna said she was bored earlier, so Anna's going to help us take this derivative. All right. So, oh wait, got to write it down first, okay? If who? Oh, now he's dead, yeah. Sadly, yes. He died back in the 90s, I want to say.
What?
Well,
Do you ever picture?
Excuse me.
Is there a picture of Dr. Seuss?
All right,
His core?
Anna, ready, here we go. So, if we want to find the intervals of concavity, right, based on what we just wrote here, right, f is concave up when f prime prime is greater than 0, f is concave down when f prime prime is less than 0, what do you think we need to find?
Second derivative.
F prime prime, that's right. So, to find f prime prime, we first have to find f prime, right? So what is f prime here? Anna? 4x cubed, minus 12x squared. Beautiful. And now we're going to find f prime prime, Anna? Wonderful. All right, now at this point, we want to figure out when our second derivative is positive and when it's negative, right? So this is very similar to how we did like the increasing and decreasing, right? So to figure out when my second derivative is positive or when it's negative, I can check to see where it changes. So to go from positive to negative or negative to positive, what number do I have to go through? 0, that's right. So Anna, what do I want to do now with the second derivative? Set equal to 0, that's right, exactly right. Okay. It's kind of like basically finding the critical points of the second derivative. So we also would want to check where the second derivative is undefined, but is the second derivative ever going to be undefined? No, that's right, Christian. All right, so Anna, we set equal to 0. Now what? Do I add 24x to each side?
No, you see that.
Very good. We factor. Yes, do not add 24x to each side. So factor out of 12x, we're left with x minus 2. And so then this is equal to 0 when 12x equals 0 or when x minus 2 equals 0. So in other words, when x is 0 or x equals 2. Okay, and then we make our little number line, just like before, except now we're evaluating f prime prime. And I'm going to label it as such, because later there will be problems where we both evaluate where it's increasing, decreasing, and concave up, concave down. So you're going to have two different number lines. You want to make sure you label it accurately for yourself. All right, Anna, pick some numbers for our intervals here.
-1.
F prime prime and -1, sorry?
And then 1.
Okay, 1 and 3. Okay, great. So we're going to plug these numbers back into the second derivative. Now, Anna has a lot of choices, right? She could plug it into 12x squared minus 24x. She could plug it into 12x, not a lot, she has 2. 12x times x minus 2, all right? Anna, I'm going to recommend you use this one, okay, because all we're looking for is the sign. So, for example, when I plug -1 into 12x, is that going to be a negative or positive answer? So negative. And if I plug -1 into x minus 2, that's going to be negative. So a negative times a negative is positive for that interval. All right, let's plug in 1. 12 times 1, positive. 1 minus 2, Anna, is negative. So positive times a negative is negative. And then these just alternate, right? So I can just go ahead and put a plus right here.
Should probably check, just to be sure.
That's right. We need to check, okay? They don't always alternate, folks. So it probably will in this case. 90% of the time it does, but we have to check. So 3 times 12 is positive. 3 minus 2 is positive. Positive times positive is positive. Positive. Okay? So with this analysis, then, we can safely say that f is concave up for what interval there, Anna?
From 0.
From 0 to 2? Concave up from 0 to 2?
Oh, no, from the -2.
Yes. 2 to infinity, that's right. And then we can say f is concave down. For what interval? 0 to 2. Okay? If we were asked to justify, we weren't asked to justify, but if we were asked to justify, we would say f is concave up on these two intervals because, and this is for anybody here, because why? On those intervals,
Second derivative.
you can say f prime prime, because f prime prime, and that's okay, that's why we're practicing now, okay? F prime prime is positive, okay, on those intervals. That was our analysis. That is a sufficient justification. Okay? How we justify f being concave down on that interval? Because f prime is negative. F prime prime, sorry, is negative on those intervals. Okay? So folks, again, I mean, that's a point right there. Okay? F prime prime is negative. I think everyone in here is very capable of making sure that they include that little justification, right, as a little sentence for concavity. Okay, very doable. F prime is negative. Sometimes I repeat myself. This bears repeating. Okay? We're good there? Yeah? Okay, let's try another one. Oh, right. That guy. All right, determine the open intervals on which the graph of f of x equal to e to the negative x squared over 2 is concave up or concave down, e to the negative x squared over 2 power. E to the power of negative x squared over 2. It's calculus. It's guaranteed to be fun.
Yeah, okay.
E to the negative x squared over 2. E to the negative x squared over 2. That's my YouTube viewers who don't have as good resolution on their screen, so they'll have to...
I'll have a worse resolution.
That's right, a zoomed-in worse resolution. That's true, it really wouldn't help, would it? I have to do something like this.
I think it's like the one above 144p.
Yeah, it's not great.
Or you could come to class.
Okay, yeah. Or you just come to my class.
Or you could just get better internet.
Okay, anywho, let's take the derivative here, right? So, f prime of x. What's the derivative of e to the something? E to the something. Times the derivative of that something. Okay. The derivative of negative x squared over 2. Well, remember, negative x squared over 2 is the same thing as negative 1/2 x squared. So what's the derivative of this thing?
Negative x.
Just negative x to the negative 1, because it's going to be 2 times negative 1/2, so that's negative 1, and then x. So it's just, negative x. Okay, so this is negative x e to the negative x squared over 2. And then what's the matter, Brandon? That's right, Brandon! Oh, man, that's our lucky day. It almost looked easy. It almost looked too easy. You know, it's like, just like one of those, like, come on, Mr. Witt. Get one of the elementary schools over there to come over and do that derivative for us.
Yeah, okay. I think when I was in elementary school, I didn't even imagine
I bet we can get some fifth graders, though, to like take the derivative of some polynomials pretty easily, because it's just like multiplication and moving numbers around, you know what I mean?
Yeah.
Like, we could teach, now they would have no idea what it means.
Yeah, they wouldn't understand.
Right? And if they saw trig, they would cry, probably, but
Yeah.
they could take the derivative of some polynomials, I bet.
As soon as I threw a sign in there, they'd be like,
All right.
feel like a variable.
All right, so here's the first and the second. All right, so let's take the derivative. So it's the first times the derivative of the second. The good news is we already know the derivative of e to the negative x squared over 2 is, it's this thing, right? That's what we just did. So it's going to be like, I don't really even have to like write it out. Okay. Plus the second times the derivative of the first, so times negative 1. That is a hot mess. This is what we would see. Mr. Whitmire gives this to you on a quiz with like some sines and cosines thrown in or something, you know? That's right. All right. What can we do at this point?
Simplify.
Okay, so we can simplify some. So I have like a negative times a negative. I get x squared e to the negative x squared over 2 minus e to the negative x squared over 2. And we want to set that equal to 0.
Hang on, I'm going to pull out the e to the negative x
Right,
squared over 2.
factor out. Common factor there, e to the negative x squared over 2. Now we're left with x squared minus 1 in parentheses. Oh, that's nice.
So then 0 equals x squared minus 1.
Right, so we set each factor equal to 0.
Equals plus or minus.
So yeah, x equals plus or minus 1.
Didn't even finish the problem yet.
When does 0 equal e to the negative x squared over 2?
Never.
Yeah, never, right? We're taking e, we're raising it to a power and trying to make it 0. E cannot multiply by itself to give us 0, right? To get 0, you have to multiply by 0 somewhere.
Sure,
So this
tried
is
hard enough we could.
never...
I bet if I beat it with a stick, I could.
Okay, so now we set up our number line. F prime prime.
Maybe, yeah.
We're going to put -1 first, right? Because that comes first in the number line, then +1, right? Order matters. All right, and now we're going to guess and check points. So, what's a good number to pick in here? Sure, -2. And how about in here? Good. And then we'll say, yeah, I know, right? Someone, there's got to be the jokesters, right? Connor's going to calculate f prime prime of pi, okay? For this one, Connor's going to do f prime prime of pi if he wants to, so there you go, that's good. Actually, he could probably still figure it out without. Anywho, let's plug in -2. So the good news is, this e to the something, this e to the something is always going to be what?
It's always going to be a
E is a positive 2.6, and we're raising it to a power. So this thing is always going to be what?
positive.
It will always be positive. So really, the only thing that's going to affect whether we're positive or negative is going to be this guy right here. So if I plug in -2, -2 squared is 4, positive 4, -1 is positive 3. So positive. Or you can say positive if we want to there, right? So this thing is positive for that interval. How about 0? Again, that's going to be positive, but then that will be negative, so it's negative. And then it's going to be positive, positive again, and so positive. Okay? All right.
Caleb, please leave.
I was going to say, if you want to go get a drink of water, that'd be great, yeah.
Get out!
Sounds bad.
Need some new, lungs. Probably just need to, completely remove the side.
Matt, can you take his lung and go get it?
So I need to trick anatomy.
Yes, Mr. Witt, I will take his lung. All right. Concave up for what intervals here? Yeah, -2. Sorry, Brittany, yeah? -1, union. 1, 2, 3. We got that dog out of here, folks, if that's what you can't tell. The dog is gone now. Caleb's returned. He took cover of that dog. Yeah, you had a Snickers. There you go. This YouTube video brought to you by Snickers. All right, and concave down for what interval? Okay. So there's your concavity. All right.
Oh no, continue.
All right, now Brittany's coughing. She's got a dog.
I remember who it was. I think it was JC or something. Was really sick and always just walked down the hallway, just coughing like that the whole way.
Okay.
Why you could hear him? Oh yeah, it was Brian.
We're going to start one more and see how far we get. We're not going to have enough time, I don't think.
It was in 7th or 8th grade.
We might have enough time.
Oh my god, it was so weird. And he was just walked down the hallway.
I might.
From all the way down the hallway.
No, I want to hit this last problem. I know, right? I know, but I want to hit this last problem because it's a doozy. All right, last one, and it's going to take us probably the rest of class. I'm sorry, but it's.
So wait, if we do this last problem, you can't get this one.
Okay.
Mr. Wood's yes, I can.
Okay.
I'm not gonna have enough room, man. I'm just gonna...
Roughly. A little bit longer, maybe.
How much room do I have?
This many.
I can squeeze it.
Yeah, you can probably just fit it in one of those margins or Mr. Wood, I just want to tell you that I would much rather take another block of this class than go and take a part in English.
There you go, see? But now you get to do both.
Two natural log of the absolute value of x squared plus
This one?
Oh, Arctangent. Oh my god.
Does that say Arctangent?
Yes, it does.
Damn, that's a good one.
Yeah, that's why I wanted to do this one, okay?
Funny joke, Mr. Wood.
No, it's not a joke.
We should write an essay about what George Washington would say about the Monroe Doctrine.
What'd it say about the, okay, and?
Like,
We had to read 3 articles about.
I'm pretty sure, didn't he, like, wasn't he an isolationist? Like, he thought we should be an isolationist, right?
Yeah.
So Monroe Doctrine said,
like, he agrees with some of it.
yeah.
And you're writing to like a museum is like the...
Dear museum. All right, anyway.
We shouldn't be involved in all these foreign affairs.
So, right, yeah. Okay, so we went to determine the concavity, which means we need to find the
Derivative.
second derivative. But first, the first derivative.
Don't get ahead of yourself. Arctangent, are you kidding me?
Yes, no, I'm not kidding.
Joke's on you, I don't remember how to do this.
Okay. So, the derivative of natural log, that's okay. The derivative of natural log is 1 over. So we have 2 times 1 over x squared plus 1
Times that thing.
times the derivative of what's inside, 2x. All right. Plus 3 times, what's the derivative of arctangent?
1 over.
You can use square. No.
No.
It's u squared plus 1, yes. It's what's inside, so you use x, so it's x squared plus 1. That's the arctangent is the easiest one. It's 1 over x squared plus 1. No square roots or anything. Yeah, arc sine is 1 over the square root of 1 minus u squared times u prime. Then, okay.
I've got one of those chin hairs.
All right,
I don't know
folks.
if I should pull it out.
Let's listen up because we're not done yet. So, look at this. It actually turned out to be really nice, right? 2 times 2x is 4x over x squared plus 1. 3 times 1 over x squared plus 1 is just 3 over x squared plus 1. And look, it's already a common denominator for us.
We're doing
Yes.
the multiplier by 2x though?
Yeah, is it? How do you pronounce
So, what's the derivative of what's inside? The derivative of what's inside the arctangent is just 1. Okay? So, again, the formula for the derivative of arctangent, so d dx, real quick here, of the arctangent of something is 1 over that something squared plus 1 times the derivative of that something. Okay? The u squared is, the square part there, Mac and Connor, is part of the derivative itself. It was not in the original problem, so it's just times what's the derivative of what's inside, which is just then 1 in this case. So it's actually really nice. It's just 4x plus 3 over x squared plus 1. That actually worked out really well. And now we get to take the second derivative,
Which is not as...
which is going to require us to use
Oh, no.
the quotient rule. So it's the bottom, low, d high minus high, whoops, d low, over the square of what's below.
You kid, you're new.
Okay, so there it is. Okay. Does this simplify it all? Emma, what do you think?
Yeah.
Yeah, okay, what can we do here, Emma?
Multiply the 4.
Okay, so we get,
4 x squared plus 4
uh-huh,
minus
yeah, that's right,
x squared
minus 8x squared, okay, great.
plus x.
Close. The minus distributes both to the 4x and to the plus 3 there. I don't know if you could read that, maybe that was not clear enough, but it distributes to both terms. So it's minus 4x minus 3, and the 2x then distributes 2. So watch that. Otherwise, good there. Okay, great. And then what, Emma?
No.
We have some more like terms in there.
Subtract the 4x.
Yeah, minus 8x squared, and we get
Negative 4x.
negative 4x squared. I'm going to put it in order here. I'm going to put it minus 6x and then plus the 4 there, yeah? Okay, great. And now we want to know when this thing is equal to 0. Okay, so we're going to set Negative 4x squared minus 6x plus 4 equal to 0. What else do we want to check? We want to check when it's undefined, right? So x squared plus 1, quantity squared, when does that equal 0? Okay. So, right, let's do the denominator first because that's easier, right? We're going to square root both sides. You get x squared plus 1 equals 0. We're going to get x squared equals negative 1. And that's going to leave us with what? Square root of negative 1, which is imaginary, and we keep it real. Keep it real, folks. Okay? So, what about this guy right here? Or this girl? I don't know. It's hard to tell. This gender-fluid polynomial. Okay? Factor out of 2, right? So you can factor 2 out, get negative 2x squared minus 3x plus 2 equals 0. I just divided both sides by 2 because 0 divided by 2 is still 2. So, or it's still 0, I mean, so there you go. Alright? Then we got to factor this. Alright, I'm gonna multiply this both sides by negative 1 because I don't like having a negative leading coefficient in my squared terms. So I'll make that, and that. Okay, does this factor?
Yes.
Yes, so we know one has to be 2x and one has to be x. So it should be 2x.
Minus 4 plus 1.
Yeah.
It's got to be minus 4 plus 1. I think it's that won't multiply to make negative 2 though. Did you factor?
I didn't take out.
You didn't factor, so again, yes, yeah, that's probably right for you. For mine, the way I have it set up, it's going to be 2x minus 1 and x plus 2. Okay, so you get 2x minus 1 equals 0. We get x plus 2 equals 0. So you get x equals 1/2, and x equals negative 2. You can see these problems take some more time because you have to take second derivatives and things, and second derivatives get more messy. All right. So then, f prime prime, number line. Negative 2, then 1/2. Yes, negative 2 is less than 1/2, so we're going to put that first and then the 1/2. All right, we'll pick up some numbers here. F prime prime of 3, f prime prime of 0, f prime prime of 1. Okay.
Shouldn't that be negative 3?
Yes. Negative 3.
You don't have to put it into the denominator because it's all it's going to be.
Right, so good point there. So Caleb, and you guys, this is important for you because, again, looking at something like this, it's kind of intimidating to think about plugging negative 3 in here and trying to figure out what sign it will be, but Caleb correctly identified that the denominator will always be what? Positive. And so the only thing that's going to really govern whether our... Anywho, we'll finish this up tomorrow. All right, your homework.
Just a reminder, students should be reporting to their third period class. First lunch will not begin until 11:15. The following students who report to the front office: Caitlin MacArthur, Justin Smith, Zach Spitely, and Kathleen Duffy.
Ooh, I don't know if I like that. No, you're not home.
Alright, someone posted in the calc chat, I'm not.
Oh, wait. If you're taking the
I'll
part,
send it out as a remind.
if you're taking the part, you just shit.
I'll send it out as a remind, everybody.
Thank God. Oh my God, I get some straight to lunch, that's awesome.